In this video, we're going to discuss the linear model. A line, the linear model, um, it can have the three different forms. So remember in our previous study that the the point slope form of an equation for a line is given by y minus y1 is equal to m times x minus x1. The second form is called general form, and then this last form is slope-intercept form, and that is the form of a line for the linear model that we are going to focus on in this video. Okay, so I want to take a minute and explain what y equals mx plus b looks like graphically. Okay, so well, of course we can obtain a line, and we're going to call that line, or that line is going to represent a function of x, which we can identify as y, and that we have identified to be mx plus b. Okay, and now I have some various things down here at the bottom that I'm going to rearrange. First thing is I want to determine b. What is b? Well, b in our equation for the in the equation for a line is the y-intercept. So I can put this right on the y-axis where it intersects, and that'll be our b value. So b you can think of as kind of our initial or starting value. So it starts at b and then it'll continue. In this case, it'll continue in an upward fashion as we go to the right as we go to the right. Okay. Next thing is I have four other things down here. I have a, f of a plus 1, f of a plus 1. And so this represents a, and then this would be the y value associated with it, and similarly for these two. So if I put a on my horizontal axis, this represents a value of the dependent variable, or the dependent quantity, rather. So if I put that here, and I'm going to just make a tick mark, and I'm going to call that value a, and then this value over here, this should be a plus 1. So if I were to add 1 unit to a, I would land here. Okay, and now as I follow these up to the line, okay, whatever value I hit on the line, if I go over to the other axis, that should be the image or the function value of a. Okay, and then so I'll do the same thing over on this one. So right here, and then if I go over, that should be f of a plus 1. Okay, but in our equation for a line, we don't discuss f of a and f of a plus, or f of a and f of a plus 1. Instead, we discuss m. M we know to be the slope of the line, but we want to describe this with a little bit more precision. Okay, so m, the slope of the line, remember, is the measure of the steepness of the line. So if I make a triangle out of this, in the horizontal direction, I have changed just by 1 unit. I have increased a by 1 unit. But then the question becomes, how far did I increase vertically? And the key to that, well, you don't exactly know what this is, but we do remember that the slope of the line is m. And so in order to, if we go over 1 unit, we need to, if we remember, slope is the rise over the run. That should be, well, we know our run is 1, and in order to maintain equality, that should be m, so this changes just m. So the way we interpret a line is that the slope is for a 1 unit increase in the independent variable, the dependent variable, the function value or the y value, increases by m. Okay, and so graphically that's how we interpret a linear model. And now algebraically, we kind of did this as we've been walking through this, but x is just the independent quantity. y is the dependent quantity, b is our starting value or initial value, and then m is the rate of m we call the slope, but really what we want to identify it as in a modeling or from a modeling point of view is a rate of change or a constant of proportionality. So if we increase the independent variable by this amount, um, the dependent variable will increase by a factor, meaning a multiple of m. And then in our linear model, the rate of change is either going to be zero or it's going to be constant. And we'll talk about cases where it is not constant. That'll actually be when we get to nonlinear models. Okay, so let's see, or let's try and use some of this in an example. So on a straight highway, a car is accelerating at a constant rate of 2 miles per hour. Okay, the units sound kind of weird. That's just to make sure that everything comes out okay. From a current speed of 30 miles per hour. Okay, first of all, is a linear model appropriate? Well, if I graph this, I know that if I look at the function, or as I look at the, rather, if I look at the velocity or the speed of the car at at time t. So if I think of my vertical axis as velocity, I'm going to use v for velocity, and my horizontal axis is time t. I should have something that looks like this because, and imagine that's a straight line, because it's saying, well, I start at 30, and then after that, I increase at a constant rate. So really, constant rate is signals to us that, hey, this is a line. Okay, because we have a constant rate of change. The constant of proportionality is 2. Okay, so I'm not going to write down an answer to this, but yes, it is appropriate, and why? Because we have a constant rate of change. So now I want to introduce notation, okay, and then I want to write a mathematical equation describing the rate of change in this problem, okay. Well, I've also started that here, but if I'm going to use v to mean the velocity, okay, and I should really say, I should really not have just v here, I should have v of t to denote the velocity at time t, and then subsequently t is just going to equal time. Okay. Alright, so the second part of the question says to write a mathematical equation describing the rate of change in this problem. Well, what is changing? The car is accelerating, so if it's accelerating, that means the speed or the velocity that I'm experiencing is increasing at 2 miles per hour. And again, that's just a unit, so really we could say that the velocity is increasing at 2 miles an hour. So and I'm going to use v and prime. We'll see why we use the prime notation in a minute, but the change in velocity is just 2 miles per hour. Again, but when we talk about velocity is in units of miles per hour. When we talk about acceleration, that unit is miles per hour. So that's why there's a little bit of a change here. All right, so in part C, and so part B, we're done. V prime is just 2. Now C, we want to write an equation describing the velocity at time t after beginning the acceleration. So really what I'm saying is, hey, what is the equation of this line? Okay, and we kind of already started it. So velocity at time t. Well, I know I started out at 30 miles an hour. The car started at 30 miles an hour. That was my initial speed. Okay, but then to this, the car began accelerating, so I have to add to this speed, okay? And now if I go back, I need to figure out, well, I need to know what my value of m is, and then I'll just have my times my independent quantity t. Well, m here is the constant of proportionality, remember, or the rate of change. We identified the rate of change as 2, so that becomes our value of m. So really, the model that we should use here is v of t is equal to 30 plus 2t. Okay, and that will be, again, the equation of this line. Okay, lastly, suppose our car gets a flat tire at time is 3, which causes a deceleration proportional to their speed. Okay, let's hang on to that. Proportional to their current speed. You assume that the car is no longer accelerating, and really, if you get a flat tire, you probably don't want to accelerate. So we want to write an equation describing the new rate of change. Okay, well, the rate of change, again, we're looking at speed. So we're going to say, okay, the change in speed is equal to something. Okay, now we have to interpret this proportional to. This, from our review, proportional to is the same as varies directly as. Okay, so that means that there's going to be some constant, I'm going to call k, and then we need to figure out how to represent their current speed. Well, their current speed, or their current velocity, is just v. Okay, so this, now my question for you is this a linear model? The answer should be no, because since velocity, their speed, is constantly changing, this whole thing is constantly changing, and this is not going to end up being a linear equation, or follow a linear model. We will see this in the nonlinear section. So that's a brief walkthrough of linear modeling. Stay tuned for more videos.